Thank you, James, and thank you to the committee for giving me the opportunity to talk about this. I'd just like to acknowledge that there's a team behind this. It's not just me, and these people have all played their role in getting this information to you. Agriculture is back in the news, and the reason behind it is primarily the UN FAO, Food and Agriculture Organization, have conservatively estimated that by 2050 we're going to have to be producing 60% more than what we're producing today. And most of that will have to come out of increased production per hectare. So the question is, internationally, is that happening? And recent research is saying no, that in all the major food-producing areas, production seems to have plateaued. It is growing in some of the developing countries, and that's where it needs to grow, but that's not going to be enough. What about Australia? Well, in the 13 years to 2011, we've increased the amount of land cropped to wheat by 1.5% per year on average, but we've only increased production by 1%. So this means that actually our productivity has gone backwards. Now that could be partly because of the bad weather we've had, but isn't. So the big opportunity for improving production per hectare is closing the gap between what current environment, current best practice management, current varieties allow us to produce and what farmers are on average producing now. And this paper is about defining for Australia, and the emphasis here will be locally and in the northern region, but defining for Australia how big that opportunity is. How much can we produce with current technology? Now technology will increase and that will allow us to produce even more, but how much can we currently produce more than we're producing? And to talk about that, I need to introduce the concept of the exploitable yield gap. And there are a number of components to that. So the first is what you see up there, which is water limited yield. We're talking about dryland agriculture here. So this is limited by rainfall, by the environment, temperature, radiation, etc., by the soil type that you're on, but not by nutrients and not by best practice. So that's the assumption. How much could you produce in any point if you introduce best practice, current best practice and best varieties? That's your water limited yield. Now, I'm sure you're all thinking, well, yeah, if economics didn't come into it, we might be able to produce that because there's a diminishing rate of return. As you add your next kilo of N, you're going to get less and less for every further kilo that you add. So because of that, people have analysed that question and they've come up with a rule of thumb that says that it's something like 80% in dryland agriculture, so 75 to 85% across a range of environments. And just recently, there's some work with Harm van Ries, which is currently in review, where he's worked out for 3 farmers with records of 16 to 20 years that these farmers have achieved 80% consistently over those years. So that's what we're aiming for. It's not the full, but it's 80%. Against that, there is what is the yield on average that's being produced, whether it be in a shire, in a region, or nationally or internationally. What is that average yield for that crop? And the difference between 80% of water limited yield and average yield is what we consider the exploitable yield gap. Now you could argue around plus or minus 5% whether that's what it is, but we've settled on that middle number, and that's what we're looking at. Okay, the methodology for this is quite complex, but I'll just try and take you through the key points. So we've based the analysis on a 15-year period, long enough to allow for most of the climate variability that takes place, but not so long as to have significant technological change affect the numbers. The actual yields were calculated from ABS and ABARE data. The water limited yield was simulated using APSIM, and we chose APSIM because it has been very well and truly validated throughout Australia. And we determined it by simulating a continuous wheat crop. So that means basically that we're looking at both what happens in crop and what happens in the fallow period, and we're assuming one crop per year. And I'm aware that in the northern region that's a simplifying assumption, but we can talk about that later. The soil data is derived from two main sources: ASRIS, which is a detailed map of soils in Australia, and AppSoil, where lots and lots of about 1,000 points of data have been derived in the Australian grain belt. We made those simulations for each met station in the grain zone, and for each met station we looked, so the average distance between met stations in the grain zone is 17 kilometres, so we took a 17 kilometre radius for each met station. We looked at the three dominant soil types and we did the simulation for each of those. We also looked at 5 maturity groups for wheat varieties to select the one that was the most suitable maturity group for any weather station. And to do that, we did nearly 60,000 simulations. And we end up with a whole lot of dot points, and those dot points have to be smoothed out, and we use a technique called local kriging to do that. It's important that our determination of actual yield and water limited yield or water limited potential are completely independently estimated from each other. This just shows you, the blue dots show you where the dominant land use is wheat, and the diamond brownish coloured dots are the dominant, each represent a weather station, and the colour in those is the dominant soil type. Now I know you can't read that, so I've just made a quick summary of the soil types in the northern region that we identified by this. 72% of vertisols, chromosols and dermasols and sotosols make up 95%. So these are the soil types we're primarily dealing with, but the other ones also get a Guernsey where they appear. So I'll just focus now on Moree Plains, just south and west of here, I guess. And these numbers, these colours that you're looking at, represent the numbers for actual yield, and I don't know if those in the back can read these numbers, but the range is, the very light colour is less than 1.4 tonnes, and the really darker green is 2.4. And as you can see, there's quite a lot of variability from year to year, which you'd expect. You can see the good, the bad and the ugly in terms of actual yield. Now the next one is the water limited yield potential. I'm using the same colours, but what you should notice is that the scale is almost double. Okay, so now we're looking at 2.6 as the very light colour, less than 2.6, and more than 4.5 as the heaviest colour. Okay, so the yield gap is basically the difference between the two maps two sets of maps that I've just shown. And here we're looking at a scale from the very light yellowy colour is less than 1 tonne, and years like 2003 would be an example of that. And the very dark red colour is more than 2.4 tonnes. And there's quite a few years that you can see that takes place in. When I was talking about what is exploitable, I was talking about relative yields. So it's important to also be able to convert those numbers into relative numbers. And that's simply the actual yield divided by the water limited yield potential and turned into a percentage. And what you can see here is that the very dark colours, like say 2000, years when the relative yield was actually less than 43% of the water limited potential. And the very light colours, when the relative yield was more than 63%. Now remember, what we want to see there is 80% or 75%. And this is just taking out the noise of year-to-year variation and giving you the average numbers. And the average actual yield for the Moree Plains is somewhere between 1.9 and 2.1. The water limited yield is somewhere between 3.6 and 4.1. The absolute yield gap is around 1.8 to 2.1 tonnes per hectare. And in relative terms, that's something between 49% and 53%. Now, this is just one example, of course, one shire, if you like, one statistical local area. This is the same information zooming out to the whole of the northern region. And you can, I guess, put the example we had there in context, so actually sort of to the south, we're looking at even bigger yield gaps. And this is taking it out to every shire in Australia where more than 5,000 tonnes per hectare, more than 5,000 hectares of wheat exist. And this is putting numbers on those maps. If we focus first on the northern region, on average, over this 15-year period, the actual yield is about 1.7 tonnes per hectare, water limited yield about 1.6, and the difference, the yield gap is 1.9 tonnes per hectare. So the relative yield being achieved is 46.6. The exploitable yield gap, which is less than the 1.9, is about 1.2. And if you then work out at $250 per tonne, that's worth nearly $300 per hectare per year. And if you multiply that by the area of wheat in the northern region, you get about $1.7 billion per year is the value of the yield gap. That's what's being left behind. I've also looked, GRDC had a survey of 1,300 farmers that they published a year or two ago. And for the average grain producer, this, just for wheat, means more than $300,000 per farm per year. Just, it's important to look at the northern region also in the national context. And it seems as though the northern region actually has the largest yield gap per hectare. The western region has the smallest, and it's not because the actual yield is higher, it's because they're achieving that actual yield with a lower yield potential. And when you multiply that by areas, then the biggest gap is in the southern region, but that's primarily because of the area. Actually, the southern region is pretty close to the national average. So the main points of conclusion are that yes, the yield gap does vary from year to year, as does production, but there is actually no trend over that 15-year period to show that we're closing the yield gap or that it's getting wider. So despite the variation in year to year, there's no trend in time in the yield gap itself. The farmers in the northern region are averaging about 47% of the water limited yield potential, and that's below the national average of 52%. The potential benefit from closing the exploitable yield gap is about $1.7 billion per year, and that's pure export dollars because we export the majority of our wheat anyway, and certainly any excess wheat would be exported. So these maps have now been developed fully, and CSIRO is working on a project funded by GRDC to put these maps into a user-friendly format that everyone will be able to access online and be able to benchmark their own farm's productivity against both the Shire yield and the Shire's water limited potential. And we hope that people will find that a stimulating challenge to themselves, both as producers and especially as consultants. And I guess I'm challenging all the consultants here to view this as a challenge and to see if they can actually diagnose the causes of those yield gaps for their producers. Thank you. Basically, ABS every 5 years, and they used to do it a lot more often than that, but now every 5 years, ABS are surveying every farmer about how much of every crop they've sown, how much they've harvested, how much is sold, how much is kept on farm. That's a very detailed study that they do every 5 years. ABARES every year sample every region where they get for what they call a region, which is a number of statistical subdivisions. They get a number of farmers that they question the same things of, and these are the numbers that make up, I guess, the raw material for calculating what that is. The numbers per shire in a non-survey year are a bit small, and so I was actually concerned how reliable they were. And so what we did is we actually looked at the 17 years where we had both the ABARES and the ABS data and did some correlations. And we generally find very, very high correlation, surprisingly high correlation. And I think one of the things I think about is it takes a survey of about 2,000 voters to work out who's going to win an election out of 5 million voters or whatever we have. So I'm fairly relaxed that whilst there may be some error around each one of these numbers, when you look at the 217 or whatever shires, the picture is so consistent that I'm fairly relaxed that their numbers are pretty accurate. We've actually translated this into water use efficiencies, but we haven't done the analysis yet. Yeah, certainly there is a correlation, but I think especially in the northern region, a really important part of the yield gap, I think, is the efficiency of the fallow period. More so than say in the southern and western region, where it's probably more to do with timely sowing and the correct rates of N, it seems to me that and this is an analysis we will complete, but from just looking at the numbers, that a lot of it is to do with how efficiently we store water over summer. The yield gap is very highly correlated with the water limited yield potential. And at first I found this surprising, because I would have thought that higher yield areas would be, I guess, more reliable and therefore encourage people to chase yield more. It doesn't seem to be the case, and we're looking at why that is. And Oswald Marinoni is, well, he's a geographer but also an economist on our team, who's looking at this in greater detail and comparing this to the socioeconomic data of farmers in the different areas to see if there is a pattern in that. When Harm and I looked closely at the Wimmera and Mallee, again, we were a bit surprised that the yield gap is greater in the Wimmera, which is a much safer area than in the Mallee. And the kind of thinking we had was around equity, farm size of machinery, all seemed to indicate towards the Mallee farmers rather than the Wimmera farmers, as having to make every post a winner. So, yeah, I think that's a very worthwhile thing to question, and also to compare internationally. You know, yield gaps between Australia and Argentina with fairly similar climates. What's behind that? I think the first one was about wet year, 98, and I've thought long and hard about that one too, because I'm aware of that. Certainly, that would be one of a number of cases where the model would overestimate. The question is, did you lose your yield though because of not being able to harvest a crop, or actual waterlogging damage, or disease? And I think a big part of it was actually disease in that year. But certainly APSIM doesn't fully account for every single thing that could affect yield, and in some years it may overestimate the yield potential. The second question was about subsoil constraints, and that's where we don't just rely on the ESRIS mapping, but we rely on AppSoil as well. And in AppSoil we actually do account for subsoil constraints, and so that will average out because we use every one of those soil types that we have in AppSoil to work out what on average would be the subsoil constraint. And the fourth one, 2002. 2002 is a low yield gap year, and in general around Australia, we did a reasonable job of simulating yields in 2002. So again, individual points might vary, but I'm fairly relaxed that we haven't got a big error around 2002 either.